All right, welcome to section 10.2 on parabolas. This is probably going to be between 4 and 5 videos. I haven't planned it out completely, but in the first, the what progression is that explain what a parabola is from the perspective of conic sections or analytical geometry, and then move from that into the different types of parabolas that you can encounter, at least at the preliminary stages at the very beginning, and then finally go into some example problems where you have equations and you have to convert them into parabolas, or you have characteristics of the parabola and you have to convert it into the equation of the parabola. All right, so let's start off with what is a parabola. So the definition from a conic section, or if you go back even before conic sections into quadratics, you guys would say probably that U shape. So you'd say a parabola is that thing that kind of looks like that. And that's true, but when you take a look at it from the perspective of analytical geometry, it's based upon distance. And what we say is that it's a set of points on a plane that are equidistant to a common point and a common line. So to look at this, the first thing we want to do is draw a point, right? So a common point. And then after that, we also want to draw a line. And then we're going to find a bunch of points that satisfy that definition. We need to find a set of points that are equidistant to both this guy here and this line right here. So let's try to come up with some points. My first point is going to be right here. And when I take a look at it, if I look at this, if the distance from the point, the common point to this, is equal to this point to this line, then we're going to say that this point is on the parabola. But when you look at it, it kind of looks like the point, that yellow point, is actually much closer to the line than the parabola. So one thing I could do is I could bump that line up, that point up to right about there, and say that and that looks like it's almost, I'd say it looks like it's a little bit farther still there. And that's really what we're going to be doing, is we're going to be trying to figure out what points we can find. Now the easiest point is this guy right here. This point, which is perfectly in the middle of this common point and this and that line. Let's see if we can get that a little bit more exact. Right there. So what we're going to say is that this point here is equidistant to the common point and equidistant to the line. Therefore, this point is on the parabola. And then we can find a couple of others. The other two, which are kind of goofy because of this, well, if I know that this right here, okay, if this right here, if I can actually measure that distance, then if I go out this way, okay, parallel to this orange line over here, sorry, that doesn't look all that parallel to that orange line right there, and go the same distance, I can get a second point. That point would be right there. But then if I do it in this direction, I can also get a second point. So essentially getting a point right here, and I'll draw them out. So if I get a point right here and a point right here, I have now 2 more points. Now why are these 2 extra points on the parabola? Well, if I measure out from here to here, this point is the same distance as it is from itself to the line. And the same thing can be stated over here, is that the distance that this point is to the common point is the same distance that they are to that common line. So our goal is to find as many of these points, or better yet, all of these points that are equidistant to both that point right there and this line right here. I'm going to go ahead and call this line D. There's a reason, we'll talk about it later. And I'm going to call this point right here point F. So as long as the points we find are equidistant to both F and line D, we're going to say that those are on the parabola. You'll notice that if I draw this point right here, that point is not equidistant. Or if I was to draw another point, let's say up over here, is that it's not equidistant to both that F and D. But if I start to find points between these guys, going straight out would not work, right? Because it looks like we are getting farther from the point but staying equidistant to the line. So what we need to do is we need to make sure that we're curving throughout. So we're going to curve up into this to probably right about there. And you'll look, that and that should be about equidistant. And if they're not, we can always bring that point down to maybe like right there. And then another point right there. And then probably another point there. And the most important thing is that all these points that we're finding are both equidistant to the focus, sorry, the F, which we will call the focus, and line D, which we'll end up calling the directrix. Now, after we get to the pink points, the 2 pink points over there, you'll notice that there are other points, but they actually don't come back around this way. And the reason they can't come back around this way is because we're going to be getting closer to the focus while we are getting farther from that line D, or the directrix. So what we want to do is we want to see, well, what happens? Well, we start to get points that are out here. And these points out here are still going to follow the definition of the parabola is going to be where this is going to be congruent to this guy over here. So as long as any point I find is both congruent to the f as it is to the line D, we're going to say that those points are on the parabola or create the parabola. And this is what our parabola would look like. So my parabola is tilted to the side specifically because when you focus on parabolas, you actually look at it only in two directions, vertical and horizontal. So I didn't want to mislead you or to put you in one of those directions as that's how they always are. So I kind of slanted it to the side a bit. All right, so some vocabulary words. The definition is based off this understanding of distance. And one of the distances we have here is this guy. This is going to be a really important distance. What we'll say is that the distance from this point right here, which I want to go back and put in yellow. Actually, let's give these guys some names. So the first thing is we're going to say that F is the focus. So in this picture right here, F is our focus. It's the focus of the parabola. Second, we're going to say that D is the directrix of the parabola. Now the directrix is actually not part of the parabola, but it defines the parabola. Very similarly as the focus is not part of it, but it defines it. So while they're useful to define the parabola, the green is actually all you really care about when graphing. It's the orange that's going to help you make that graph more accurate. Next, after those points, this guy right here, we call this guy the vertex. So we're going to label that as V. V is the vertex. And then we have those two pink points over here, that point and that point. These guys are going to be called LR1 and LR2. They're the endpoints of the lattice rectum. So LR1 and LR2 are very special points because they help us understand, not help us understand, sorry. They're actually really useful for graphing. They give us some, they're very easy to find when we're graphing, and you'll see why in a second. So we'll call these guys the endpoints of the lattice rectum. Endpoints of lattice rectum. Now you're going to want to remember the definition of lattice rectum because it's going to help you graph these things. And the definition of the lattice rectum is that it is the segment. So once again, the lattice rectum is a segment that starts and ends on the parabola, but also goes through the focus. So we're not going to draw the lattice rectum, but if you were to draw it, it would be this pink segment right here that starts on the parabola, ends on the parabola, and actually goes through the focus. Now there are lots of different lines you can draw that start on the focus, start on the parabola and end on the parabola and go through the focus. For example, you can do that one. So not only do we want to say that, we also want to say that it is parallel to the directrix. Now I know it doesn't look parallel, but we want to make sure that we understand that the lattice rectum is also parallel to the directrix. So the directrix and the lattice rectum should never cross each other. All right, the last thing I wanted to say is the relationship between all of these points here, the orange point, the yellow point, the directrix, the two pink points, and the distance between the vertex and the focus, we actually call that P. So the distance between the vertex and the focus is going to have major relevance in our graphing. So we say that it has P distance this way. But not only is it P distance this way, it also has to be P distance this way by definition of the parabola. But then if you look at it, that means this right here would have a distance of 2P, as well as this guy. This guy would have a distance of 2P. Now you might ask why, and the reason is because if you have one P in the middle and a second P up here, then that means that the directrix to the focus would be 2 P's away, which would mean that this point would be 2 P's away from the directrix, and then it would also have to be 2 P's away from the focus in both directions. And this is why you'll often hear that the lattice rectum is equal to 4P. Okay. If this doesn't make sense, go back through it. You may want to look up other videos or even read your textbook. This is just to give you a brief understanding of what the definition of a parabola is. In the next two videos, in the next video, what I'd like to do is go over the types of parabolas that you will see, going into the equation and how it's going to work with identifying the information, the lattice rectum, the directrix, the vertex, and the focus, so that you can start graphing these things.